That's the problem with I don't censor myself too fast, right? It just comes out. Well, hello and welcome back to Calculus 1. This is Chain Rule with Revenge, the second part of the lecture, where we get to mix this with product rule, quotient rule, and we need to decide which rule is the main rule, and then what rules are within. Can you have a problem that uses all of them at once? Yes. Are we going to do them? Not yet. All right? I think next week I'm going to teach the most powerful differentiation technique, which if you learn, you will be taking any derivative mentally without writing anything down. Now we're talking, right? But as it always goes in mathematics, you first, right, learn the long way, and then you keep generalizing, and then these shortcuts and really powerful stuff eventually surfaces. In linear algebra, you're going to take the entire Calc 1, 2, and 3 and write it in one formula. But that's linear algebra, right? You can take that right after Calc 2. So now we are going to take a look at the mixture between the product rule, quotient rule, and chain rule, and see which one gets to play. So if we go back to one of the problems that I stated at the beginning, we had the derivative of 2x, let's say e to the x to the 6. All right. So here is the product rule. Right? This is the product rule because we have a linear function 2x over here, and then we have exponential function e to the x to the 6. So this is definitely the product rule. This is definitely the product rule. But now when you carefully inspect the two factors in this product rule, you see that the second one is the chain, actually, because you have x to the 6 within e to the x. So this is the product rule is the boss. It's the main rule that we use to solve the problem, and then chain rule within. So product rule. Yeah, my English stopped working. So I should say chain rule within product rule. Chain rule within product rule. Product rule is the boss. So this problem here is chain rule within product rule. So product rule is the boss. Good. We know we know the formula for product rule, right? Copy the first derivative of the second and so on. Whenever we get to do derivative of this one, this is when the chain kicks in. And only on that part. The rest we follow the product rule formula. So product rule formula was copy the first derivative of the second plus copy the second derivative of the first. You see that v prime? That's when the chain rule kicks in. So the derivative is copy the first, that's 2x, and now it's time for the chain, which means e to the x to the 6 times 6x to the 5. So this part was our chain rule. And then we have plus copy the second, e to the x to the 6, times derivative of the first, which is just 2. So now let me go u, v prime, v, u prime. We can kick out 2e to the x to the 6, and what's left is 6x to the 6 plus 1. That would be the simplified version, right, when you unleash algebra upon it. We factor out 2, we factor out e. Now notice that you have an x that you didn't use, and you have x to the 5, so that's x to the 6, right? And you have this 6 in there, so 6x to the 6. You factored out everything from this term, so 1 stays as a placeholder. That was that. Now I promised that applied problem, and here we go. Much more on this. If you take differential equations, you have a pendulum and you let it swing back and forth. The distance that covers is measured with this function that does this, and it dies out in time. And this is the distance. You can call it y, you can call it d, whatever. So when you look at this particular graph, it makes sense, because as you swing and let go, when you pull it, that's this far away distance, and then when you let go, it goes one side, the other side, but every time it's less and less and less and less, and it eventually stops, right? So we have that as an experiment, right? We can do it, and then you let it go, and it eventually stops, right? So that would be the pendulum. Now the function that governs this type of motion is going to be y equals e to the, let's say, negative 3t time times the cosine, right? Because it starts there, didn't start at 0. Cosine of, let's say, 5t. Now, if you want to understand physics and all of these things, you always look at the equation and say, what is each one of these terms doing? Well, this one is the minus on t, which is the one that makes this shrink. So this is the stopping term, right? The bigger this is in terms of negative numbers, so negative 10, negative 50, negative, right, the faster it's going to stop. And then this one over here is the speed at which it moves, right? Because you can start like that, or you can start very fast, whatever. So that's the angular velocity, omega, that governs the speed. So that's the period of how fast it oscillates. Your radio signals and cell phones and all of that stuff just all changing values for this thing here. Also your colors that you see and my voice you hear different if I go oh or oh. It's just a different number in front of that t. So that's how we understand the world around us. Now this is the path for the particle, that black bob, right, that moves in this case. When I dangle this mouse, that will be the mouse, that black dot. And I know its position at all times. So if you ask me what's happening in 1 second or after 3 seconds, all I need to do is to plug 1 or 3 for the t, and I will have where the object is in space in comparison to the original position. So just by simply plugging in a time of your interest, you will know, right? And if the time is sufficiently large, obviously the answer will be approaching 0, which means object is standing still, right? It's not oscillating anymore. But we can differentiate this. And what happens if we differentiate? If we differentiate, we get last class. Acceleration. You get velocity, and then eventually you get acceleration, right? So, what is the derivative here? Yes?
Is the next one jerk and then the next one jumps?
Yes. Oh, nice. Did the research. Nice. So, we have our position function. We called it s of t last class. And now to find velocity, I need y prime, right? So velocity in time would be my y prime, and now I have to do the derivative. Now, what type of a function do I have? What rule do I have to use? It's clearly a product. Thank you. You have the function e, exponential, times the trig function cosine. So two separate functions multiplied, product is the boss. But if you take a look, you have the function negative 3t, and you have the function 5t. Those are the linear functions within, so you have two chain rules, right, when you do the derivatives of each. So let's go. Copy the first. derivative of the second, derivative of a cosine is negative sine 5t times 5, which is the chain, plus copy the second one, times derivative of the first, and then times negative 3 for the chain. So now my velocity function, y prime, is going to be what? I can kick out negative e to the negative 3t, and in parentheses I have 5 sine 5t plus 3 cosine 5t. So now if you give me that the time is 2 seconds, I will tell you the velocity of the thing at 2 seconds. Remember that velocity is measured at the instant, which is why we say instantaneous velocity, right? At every instant in your car, velocity is measured by the dial you have, right? The speedometer. As soon as you touch either gas or a brake pedal, right, it changes instantly, right? It doesn't sometimes change as fast as you would like it to change, right, when you see the woo after, but it's too late already, right? So here is the example that you asked for, where we're going to see the chain rule and the cosines and e's and exponents. And it's called a simple harmonic motion. There's nothing simple about it, but that's the name, right? Yes?
Can we do a quotient rule one?
It's coming up, Coleman. Relax. Now I feel pressured. Where's my quotient rule?
That's the scary one.
I just have a question. So with the new formula this way, like when you're combining them, like it would, and it's a product rule, like a chain rule within a product, if instead of multiplying, like the first part of it is f times g prime, so instead of multiplying g prime, are you taking the formula for the chain rule?
Aha, okay. So the way it works is you only, let's go to the previous example because it's better. You only apply chain for the little bit of the function that you are considering in a derivative. So if you take a look at this part here, its derivative, which was the chain rule, is only this part. That's those two, because you copy the first and then the derivative of the second. Well, there was the chain rule, so you do the full chain rule. Now, this particular problem you get to find up here on its standing on its own, right? Like this one, right? I have downstairs. I have e to the x to the 6 over here, x cubed. So as you can see, this entire problem now became the part of the product rule. So it's like a little box, right, that you do on the side and just plug it in. Let's do another one. So we did these two products. How about the derivative of x cubed sine x to the 9th power? All right, let's see. So, do we all see the product?
Yeah.
It's within the 9th power, right?
Yeah.
So this could be a product within the chain, right? So we start this problem as 9 x cubed sine x to the 8th, right? And then times the product rule of the inside. So now it's a product rule here, right? Because that's the derivative of the inside in the chain. And that the guts of the problem was a product rule. So now the product rule goes in there. I'm going to give you a few seconds to fix it if you missed it. And then I'm going to write it in. So you are doing the product rule between x cubed and sine x. You next. Don't panic. I promise. 100%. You. So copy the first, which is x cubed, time derivative of the second, which is cosine x, plus copy the second, sine x, times derivative of the first, which is 3x squared. Thank you. Now we make it pretty. We can kick out x squared. 9x squared. X cubed sine x, everything to the 8, times x cosine x plus 3 sine x. Can we make this even better? Sure. But, yeah. You can go 8, x cubed to the 8 is x to the 24, and then these 2x to the 26, sine x to the 8, and yeah. You can do things. Thank you for your patience. The next is your favorite quotient rule. So warm-up problem of a to the x over x squared plus 1 to the 9th power. Which rule is the boss? Chain or quotient? Chain. Chain is the boss because everything is raised to the 9. You can write that as a sentence. Chain is the boss because everything is raised to the 9th power. It's okay. We understand each other, right? Okay, let's take a look at this together now. Chain rule is first, therefore we start with 9 stuff to the 8. That's the first step, right? We have our e to the x over x squared plus 1 is guts. Now, the derivative of the inside is our quotient rule. We take denominator and square it. Then put denominator as is, times the derivative of the numerator, minus copy the numerator times derivative of the denominator. Perfect. For purposes of chapter 4, you actually do not have to fix this one, because you have it in a factored form where you can set the first one equal to 0, and because you have e to the x here and no solution, set second one equal to 0, denominator dies, right? So you just have to do this equal to 0 on a side. It's very quick for chapter 4. This particular problem you don't have to fix. However, right, we can do it just to show off. So one of those things. It's a good conversation starter. Let's say Thanksgiving dinner. Yeah. It's eventually coming up, so you can start with "by the way," and then you write this on a napkin. Especially if it's one of those linen napkins, you know, with the silver lining and yeah.
Permanent marker.
Permanent. See, now we're speaking the same language. Thank you, thank you. Exactly. Permanent marker. Death wish. Oh.
I ever did that to my mom.
Oh. I thought you are threatening.
Oh my God! I would never. I don't even kill bugs.
Well, that's nice of you. So we have this, the denominator x squared plus 1. So as you can see, I give 8 exponent to each one of them. 9 does not get the 8 exponent because it's not in the parenthesis. Over there we have e to the x, and we have x squared minus 2x plus 1 divided by x squared plus 1 squared. And now we pull all of the resources together. Yes, the denominator goes to the 10th. So we have 9e to the 9x times x squared minus 2x plus 1, everything divided by x squared plus 1 to the 10th. Just because we can. Beautiful. This does actually factor into x minus 1 squared. Yeah. Well, why not?
It's kind of cool.
9x, x minus 1 squared divided by x squared plus 1 to the 10. See, who said elementary algebra doesn't come in handy? All right? You can flex.
You can flex.
You can flex this way in math. Yeah, this is what I said to the students. Whatever formulas you tattoo on your body, I mean, you get to use it on a test. It's just, you know, there's nothing I can do about it, right? Comes in, it's like a product rule right here. It cost me $200. Okay.
It's not the worst tattoo you could get.
No, I've seen some.
I'm confused about where you got 9, e to the 9x.
Oh, when you multiply these, you add exponents. So 8x plus 1x is 9x. You have the rule x to the m times x to the n is x to the m plus n.
Yeah, but
E is a number by itself.
But what I'm confused about is that I didn't get those two those two, like, oh my god, fractions. I got what I just did 9 And then the second one.
This one. Because I took this 8 and I applied to both.
I'll work on it when I get home.
Well, we can take a look after class. Fine.
Okay.
All right. Let's do another one of these. Something fun. Relatively speaking. E to the x. No, let's not do e to the x all the time. Even though we could, but sine cubed x divided by x squared plus, put it to the x, it's okay.
Oh my God.
It's okay.